So yesterday we finished up talking about nitrogen nucleophiles. We said if you've got an aldehyde or a ketone with a primary amine, you can make an imine. We went through and we did the full mechanism for that one. And then we said with secondary amines, you can get an enamine simply because you don't want to have a charged intermediate. Today we're going to start off with a variation of using a nitrogen nucleophile called the Wolff-Kishner reduction. And I'll show you the overall transformation and then we'll jump into the mechanism. All right, so overall the mechanism uses some sort of aldehyde or ketone. And this is hydrazine. And when you run this, just like before, you typically will run this under a pH-controlled system. So pH typically about 4 or 5. And you normally try to remove water in this reaction in order to favor formation of your products. Let me fix these arrows. Will we get an imine or an enamine for this reaction? An imine. Because we've got a primary amine, we will end up forming an imine. Does anybody know the special name of this imine from yesterday's notes? It's a special type where we've got 2 nitrogens there. A hydrazone. However, if you call this an imine, I won't be upset. And then in the next step, what you want to do is treat this with strong base, something like something like potassium hydroxide, and then you will run this in water and heat. This is no longer a reversible reaction. Instead, what you do is end up completely eliminating the functionality coming off the position where the carbonyl used to be. So it's pretty handy, right? If you want to get rid of some sort of carbonyl, you can quickly convert this to a CH2 group. There's another reaction we saw previously that looks a lot like this. Does anybody remember that one? It's from our aromatic chemistry chapter. I'll give you a hint. We'll review all of these later. We could do this with aryl ketones and turn this into something like ethylbenzene. And what reagents did we need? Not quite. That was for reducing a nitro group. Is the zinc and mercury and HCl. This was the Clemmensen reduction. If you notice, the Clemmensen reduction really only works with aromatic ketones. This one will work with any ketones. It's really versatile. The other nice thing with this is it avoids using mercury, which from an environmental point of view is desirable. However, if you remember me saying this one is problematic due to acid, this one is now problematic due to the base that we have. So it's kind of pick your own adventure here. Both of them can do similar reactions.
That's still a cyclohexane.
Yep, it's still a cyclohexane ring. So now we can interconvert pretty easily between these. So let's look at the full mechanism and try to understand how we lose that functionality. All right, the first step, we're going to skip straight to our hydrazone because we already practiced making that. That was similar to your pod, right? All right, and in the next step of the Wolff-Kishner reduction, we've got hydroxide around. We've got to find the most acidic proton. Where is that going to be? Is it going to be a CH proton or an NH proton? NH, right? Going back to first term, we can follow the cardio rules. We want to pick the one that's attached to the more electronegative atom. All right, when you do this, you can actually clamp down and push electrons all the way to that carbon. And I'm going to show this as one way, and you'll see why later on in the reaction. But at this point, you've got a negative charge on that carbon. You've got your conjugate acid, which is water. And this carbon will really quickly steal a proton back from water to regenerate your base. So now we've got our base back. The base can do the same thing one more time with the remaining proton. However, now we're going to break a sigma bond. So when you do this, you end up with a negative charge on your oxygen, on your carbon. You end up with a nitrogen-nitrogen triple bond, and you end up with water floating around. All right, the key feature with this reaction is the nitrogen. The reason this is irreversible is, what do you think happens to that nitrogen? Yeah, it just bubbles out of solution. It doesn't want to go back into solution very much, so this will just bubble out. All right, and then in the next step, this carbon can steal the proton back from water to give you your final product plus your hydroxide. So it's a pretty clever reaction. Liberating nitrogen drives this out of equilibrium, and you can trap your cyclohexane or any other aryl or alkyl ketone. I did want to make a note, just say it is greener option, but can't be used if you have a base-sensitive functional group. And I'll say it's greener simply because we're avoiding mercury. There is one logistical concern with doing this reaction on a large scale, and that is the amine that's used is quite flammable. So typically this isn't done on industrial scales. Does that make sense? All right, so it's a unique way of removing carbonyl groups. All right, what I want to do is switch over and do a few practice problems before we continue on. And I've got some of these up here, and I'm going to try to make this more like an exam or a quiz. So I want you to predict the starting material for this one. I'll make this worth 4 points. We're going to treat this with a buffered system, so I'm just going to write H+. We're going to remove water from this reaction. You also need to determine any other reagents. And our final product for this reaction is going to look like this. I'm going to make this bigger. It looks kind of funny right now. All right, so see if you can figure out the missing components and try to work through this with a neighbor.
It's not an equilibrium arrow, right?
In this case, I drew minus H2O, implying we're removing water and driving it out of equilibrium.
Okay.
Yeah. I'll put a second one down too. If you get through this quickly, you can try the second one. This one also is in a buffered system. We'll remove water from the reaction mixture. nitrogen. This one looks a lot more complicated. So see if you can figure out both of these with your neighbor and fill in the missing box pieces. All right, I'll show you guys some simple tricks for deconstructing these. These look really complicated and they are tricky. First thing I always do is look at my product and decide whether or not it's an imine or an enamine. All right, so for the top one, is this product an imine or an enamine? It's an enamine, right? We've got an alkene. Oop. So it's definitely an enamine because of that double bond between two carbons, right? That's the first step. What does that mean about the amine that we're adding in? Is it primary, secondary, tertiary? It's got to be a secondary amine. All right, now what we need to do is figure out what the heck that amine is going to be. And what I like to do is look at my final product and figure out what it would be by looking at the final product. And I'd say, well, it's probably going to be this thing, right? That's a secondary amine. So what we could do is just plug that in, and we could say, it's got to be that, right? So we just kind of swap off that carbon bond for a nitrogen-hydrogen bond. Yep. It doesn't matter that much. You could put your ketone in there if you want. I wasn't being super clear. Remember that the acid here isn't just straight strong acid. It's a buffer system, but it's pH 4 to 5. Yeah. So we've got our secondary amine. Conversely, that means this portion must have been the ketone. And we need to identify where the carbon-oxygen double bond used to be. And the easiest way to say is, well, it must have been the position where the nitrogen was attached. So that's where the carbon-oxygen double bond must have been, which means our starting ketone must have looked like that. So not too bad. These look far more frightening than they actually are. So if you can, try to get used to pattern recognition and deconstruct it by doing those simple steps. All right, I'll give you a little bit of time to do this one, but I'll get you started. First things first, is this an imine or an enamine? What's that? It's a carbon-carbon double bond, right? That means it's an enamine. All right, that means that this nitrogen right here most likely attacked that carbon right there. If you notice back in that previous example, the carbonyl carbon must have been off of that red position where the nitrogen was attached. Does that make sense? So now we need to deconstruct this and figure out what the starting material must have looked like. And I will give you a hint that there is only one starting material. It's not two pieces coming together. So see if you can figure it out with your neighbor. And just for fun, let's do one more. Okay, let's do the first one, and again, I'll show you my trick. We know, because it's an enamine, that there must be a secondary amine in our starting material. And like I said, there's only one starting material here, so maybe the secondary amine is dangling off the ketone somewhere, right? All right, next thing I would do is do my imaginary cut and say the carbon-carbon bond must have been right there. So again, start building this up and say, okay, carbon-carbon bond must have been off of that red carbon like we saw before. Down here, this stuff is all pretty far away. However, this nitrogen now is over here, and this is our secondary amine that is actually reaching in and attacking itself. So you can do intramolecular reactions. The key thing, though, is first identifying whether you're making an imine, enamine, and then deconstructing it, identifying where the carbon-oxygen double bond used to be, and go from there. All right, last one for practice. Is this one an imine or an enamine? Imine, so it's different. That means over here we must have had a primary amine, right? Okay, now the question is, where must the carbon be that used to have the carbon-oxygen double bond? So talk with your neighbor and see if you agree. I would say it's got to be right here, right? Okay, that means with imines that we're still going to cut that carbon-nitrogen bond. So just like before, we would say, all right, that used to be the carbonyl. And then if we look out over here, that nitrogen must have been a primary amine. So it does take a little work to get good at these pattern recognitions, but please practice as many of these problems as you can. Historically, on this first exam, this is where people get nailed on points because they don't even know where to begin and they leave it blank. And anytime you leave something blank, you get 0 points on it. So try to get good at pattern recognition. All right, let's switch gears. We're going to do a little bit of review. We're going to look at hydrolysis reactions. And I want to review this a little bit because I always tell my students if you can do a reaction backwards, you can definitely do it forwards. So if you remember, this was our cyclic ketal. Why do we put on these cyclic ketals on carbonyl groups? To protect them, right? However, I said if you want to remove them, you can treat this with acid and water. And if you have excess water and acid, you can essentially push this out of equilibrium. You can form your ketone, and you can kick off that ethylene glycol that was protecting it, right? So the reason this is no longer in equilibrium is we're flooding it with excess water. Using Le Chatelier's principle, we know we're going to push it out, right? Okay, so now we need to do the mechanism for this. And this mechanism is just as steppy as the forward one, obviously. So bear with me. So we've got water around, we've got acid around. The first step is going to be in equilibrium, and that's going to be protonation of one of the oxygens and your cyclic ketal. Okay, now we've got to decide on the next step. We still have water floating around, so I'm going to just draw that in. What do you think happens in the next step? I'll give you a hint. This whole thing is a good leaving group, right? The oxygen is protonated, not happy being protonated. Is there any way to dump electrons to it? Second hint. We got 2 lone pairs over here. Can eject it out, right? Okay. So that's going to be our next step. Now it looks a little bit funny. Looks like this. We still have water floating around. And water can reach in and attack. Next step, we need to get rid of that proton on our water. So I'm going to quickly show a proton transfer. Oop. So I'll just say minus H plus. All right. Now we're going to pause here for a second. What do we call this intermediate? It's half alcohol, half ester. What was that? It's halfway there. What do we call something that's halfway there? Hemiketal. So at this point, we're at our hemiketal. Okay, and in our next step, we're going to move that proton around. Specifically, we're going to move it to this oxygen. Just like before, oxygens that have a positive charge can act as a leaving group. So in the next step, we need to kick off that leaving group. I'm actually going to slide this a little bit. So what do you think can kick off the leaving group? Yeah, the oxygen lone pair. So always pay attention to adjacent lone pairs, because this lone pair can clamp down and kick off that leaving group. At this point, we've made ethylene glycol. That was our entire leaving group that got launched off. And then our second product that we have looks like a protonated ketone at this point, which means in our last step, we can simply deprotonate that ketone and be left with our ethylene glycol plus acetone. Makes sense? Seems steppy. What I like to do is then do this in reverse. So we're all set up because we already drew all our intermediates. So I'm going to use a different color pen. I'm going to use my blue pen. We're going to start at the bottom and then go backwards all the way back to the beginning. So like I said, with equilibrium reactions, if you can do it backwards, you should be able to do it forward. Okay, so in the reverse reaction, we know the first step is to protonate our ketone, right? Second step, this can attack in, kick up electrons. That gets us to the same intermediate. And then in the next one, it's just a proton transfer, so we don't even need to draw an arrow. We're just deprotonating it at that point. And then in the next one, it's also a proton transfer, so we don't need to draw an arrow. And then in the next one, you can do the opposite reaction where you kick off that water. So we're kind of going in the reverse direction. And then in the next one, once we're there, it looks like we're just doing a proton transfer again, and so on. So what I like to do as practice is recommend that students practice doing a forward mechanism, and then a backwards mechanism, and then a forward mechanism, and a backwards mechanism, and do it till your head hurts. When you get to the point where you're sick and tired of doing it because it feels easy, that's when you've mastered it. Try to do a bunch of different examples, though, going both forward and backwards. That's how you get good at this. Does that make sense? It does take a little bit of time. Let's try doing the... Let me just make a note that blue equals backwards. Let's make a couple of other notes, though. This also works for imines and enamines. And I'll really quickly show you the overall transformation. We won't go through and do the full mechanism. However, I would strongly encourage you to practice it because there's a very real chance it'll show up on an exam. And this is where you have your acid. Treat this with water and excess. And in this case, we're starting with an enamine or an imine. An enamine, or sorry, an imine. Oh my goodness. An imine, which means this carbon, whoop. Let me keep it as red carbon. Used to be a carbonyl carbon. And our amine must have been a primary amine with that R group on it, right? So make sure you can do that. Alternatively, you could have an enamine. You could treat this with catalytic acid, water in excess, and just like before, identify the carbon that used to be the carbonyl carbon. So this must have also had a ketone. However, this time your nitrogen must have been a secondary nitrogen, which is why it formed an enamine in the reverse direction, right? So make sure you feel comfortable going forward and backwards with these. All right, what I want us to do, just for more practice, the remaining time, try to draw the mechanism for this overall transformation. So I'll give you guys some time to do that. We're going to hold off on sulfur nucleophiles until next week. I just wanted to get more practice in. What you can do is look at the notes from when we did the forward reaction for making an enamine. All of the intermediates will be the same. And then you got to figure out how to do the arrow pushing backwards. So let's do the mechanism as a class. The first step is going to be protonation. Now the question is, well, which carbon is going to get protonated? This is going way back to chapter 9. We always want to form our more stable carbocation, which means the proton will end up going off this carbon. We'll end up with a positive charge here, which makes sense because this is resonance stabilized and it's tertiary. That's way better. So in either situation, your goal is to always make your most stable carbocation. All right, and your next step, you've got water around. So water can reach in, kick up electrons onto that nitrogen. You now have your amine. The next step, you can deprotonate. So I'll just write minus H+. We'll lose a proton from that water. It will look like this. And now, again, we need to do a proton transfer. So I'll just write plus H+. We're going to move that proton over to the nitrogen. Okay. And in the next step, you can show this oxygen. Oops, sorry, there's no lone pair there. That should be a positive charge. And in your next step, once that's protonated, you can kick it off. At which point, you've kicked off your neutral amine. And last but not least, you can do a proton transfer. The order of proton transfers might vary a little bit in your forward versus reverse direction, but the intermediates should follow approximately the same order. Does that make sense? Whoops, I forgot one arrow, taking off that nitrogen. This takes a lot of time to practice, so please do practice problems over the weekend. Try to get a good start on your sapling as well. That way, if you have any questions or concerns, you can talk to me. We will have an exam next week. It sneaks up, and quite often students get bogged down with other work, so try to prioritize some organic chemistry this weekend.